right, so if you're ever given a situation where you have a table of values or a chart, you are very, very limited in the types of things that you can be asked and therefore answer. If you have a graph, of course, you can kind of infer values. If you have an equation, you can calculate them. But with the chart, we're limited to only the values that they're giving us. So the values of a bug, that's a little more exciting than a particle. Moving smoothly and continuously, that kind of implies that it's what? Differentiable. Yeah, differentiable. Now, most of the time, it'll say that it's a differentiable function instead of saying it's smoothly and continuous. For various values from 0 to 4, so there's no units, so we can kind of maybe assume they're seconds if that helps you, or maybe the bug moves slowly and they're hours, whatever you want. But these are the positions or velocities. Positions, it's the coordinate of a bug moving along a line. So it doesn't tell us if the line is vertical, or it doesn't tell us if it's horizontal. So it doesn't really matter. If you want to assign it to horizontal because it helps you, that's fine. But we have position values, okay? What is the displacement of the bug during the first 4 seconds? Well, that's a pretty easy one, right? Displacement, which I'll just label DISP. It's final minus initial position. So that's going to be S of 4 minus S of 0. And then we can pull those values from the chart. Hopefully they're there. So 0.2 minus 40. And that's a good place to stop if you want to. Or you can say negative 39.8 if you want to do that. So that means that what? During the 4 hours or seconds or whatever, the bug ended up 39.8 units to the left or below where it started, depending on what kind of line it's on. All right, the next one. What's the minimum number of times the bug changes directions? Explain your reasoning. So now this is pretty relevant, the fact that it's smoothly and continuously drawn. So what did y'all come up with there? How many times does it change direction? Minimum number of times. 2 times? Twice? Let me just say twice. All right, let's see. Let's kind of follow the position. We can kind of say it's moving vertically. That might be helpful because usually the Y values, are what we're measuring. So it starts at 40 and it's decreasing on average to 35. We don't know if it's monotonically increasing, right, the whole time. It could go up and then back down, but on average it's decreasing, and on average it's still decreasing. And then what happens next? On average it increased. So that should be one change, yeah? And here again, on average it's increasing, but now on average it's decreasing. So there would be a second time. And then it's on average decreasing, on average decreasing, on average decreasing. Yeah. So for sure, twice. Perhaps many, many, many more than that, correct? So twice is correct. Very good. To justify this, you can say something about the Y values decrease on average and then increase on average and then decrease again on average. Something like that. That's about as refined as we can get at this point. Later on, when we learn the mean value theorem, you could also talk about the average rates of change. The average rate of change is go from go from negative to positive and then positive to negative. And therefore, we know that the instantaneous had to do that as well. Okay, and anytime the velocity changes signs, we know it changes directions. So I'm just going to kind of leave that blank for now. We discussed it. So for now, we'll just say the position values on average decrease, then on average increase, and then on average decrease again. Okay, something to that effect. What's the bug's average velocity from 0 to 0.5? Show the work that leads to your answer. That is a very, very typical thing that you'll see on a problem. That's basically them saying, show your difference quotient. So average velocity, we'll label it. You can abbreviate like that. It's going to be your final position minus your initial position. So that's displacement, and then all over the change in time. So even though we're subtracting 0, we don't really need to show it in our head. We do need to show it on our paper. So make sure that you're showing your difference quotient. And then we just pull values out of the table, and hopefully we find that they're there, 35 and 40. Yeah, 35 minus 40. And now you can call it 0.5. So if this were a free response, which is kind of what this one looks like, right? Could you stop right there? Yeah, absolutely. Let's see what it actually equals. That gives you -5. And instead of 0.5, you might want to call that a half, because then you could stage change flip it, right? And so dividing by the half is the same as multiplying by 2, and you end up with -10. So that would be the average rate of change. We kind of talked about that up here when the bug changed direction. The average rate of change was negative, and then the average rate of change was negative again, and then the average rate of change was positive. So if you compute the average rate of change all the way across for consecutive intervals, you could actually see 2 sign changes in those to justify this right here. Yeah, cool. There's no unit, so we're good. Estimate the bug's velocity. All right, so here's another buzzword. Throughout the year, we'll kind of reinforce this. Estimate is another word for approximate. And anytime you see one of those 2 words in a question, you need to be on what I call squiggle alert. And with this voice, I can't say squiggle as funny as I normally do. But squiggle alert, okay? It's the approximation symbol, and you need to show it in your calculations. All right, so how are we going to approximate the velocity at a single point? Velocity at a single point is instantaneous, right? That's the derivative of position. We don't have an equation that we could take the derivative of to plug in, and we don't have a graph with line segments for position that we can compute slopes of. So the only way that we can find slope at a point is to estimate it or approximate it with a secant line, like we did in the very beginning of 2.1. So let's see. If we're trying to approximate the slope at 0.1, I'm going to be interested in that point. There are 3 different acceptable ways to do this, okay? If you look to the left and right, each of those are a half unit away. So the x spacing is uniform in this case. So if that is the case, if it's uniform spacing, you can use the point of interest and the point to the left. I'm going to write that up here. I'm just going to put approximately for now. That could be approximately 35 minus 40 all over 0.5 minus 0. You can use the point of interest and the one to the right. That would be this, 30.2 minus 35 all over 1 minus 0.5. Or, believe it or not, you can use the 2 points that straddle it. Okay, it's kind of like the symmetric difference quotient that your calculator uses. That would be this, approximately 30.2 minus 40 all over 1 minus 0. Okay, so those are using the numbers right out of the chart. Notice I didn't say S of whatever minus S of whatever. If you pull those Y values right out of the chart and they show up in the difference quotient, that is enough to get credit for showing your work. Now, that is not all we need. Any one of those would work, but what we really need to do is put S prime, in this case, of 0.5, and then the squiggles, okay? So the derivative is approximated by that difference quotient, or the derivative is approximated by that difference quotient, or the derivative is approximated by this difference quotient. All right, so when the point you want to approximate the slope at is in the table, and the 2 values on either side are equidistant, you have 3 options. That point and the one to the left, that point and the one to the right, or the 2 points straddling it. All right? Next one, we want to approximate the slope at 2.7. So you come up to the table and you're like, hey, 2.7 is in the chart. So you immediately say, okay, I got to use another point to approximate it. This point is 0.7 away on the left. This point over here is 0.3 on the right. So in this case, you are going to use, for acceptable answers, the point of interest and the one that's closer to it. Because the other one could be relatively far away. It could be miles and miles away. So the general practice is to use the point of interest and the one closer to it. So you would say then that S prime of 2.7, squiggles, and then make sure you're doing the Y values in the numerator, because the table that they're going to be giving you is typically given to you as a horizontal table, where you see the X values in the top and the Y values in the bottom. And it's a very easy thing if you're rushing or not thinking to do change in X over change in Y. Now, if you did change in X over change in Y, you would probably still get a check for a difference quotient, but of course you're getting the reciprocal, the right answer, not the right answer. So I'll move that down here. And then 3.5. 3.5 is in the table or not in the table? It's missing, right? Now, this is what they've been doing here in recent years, because the other two, you know, it seems almost kind of arbitrary which ones we're supposed to use. But in this case, if 3.5 is not in the table, it would fall between 3 and 3.6. So now there's one way to do it again, and you're going to use the two values that are on either side of where it would live. That's the only way to do this problem. So you would say S prime of 3.5 equals, and then again, change in Y, 16 minus 38.2, all over 3.6 minus 3. Oops. Before I walk away, I always check my answer, and what am I missing here? I'm missing the squiggles. Yep. So you could lose points for not having that when the instructions say estimate or approximate. But that's a 2-for-1 right there. That gets you your difference quotient check for indicating your method, and it's also a numeric answer, so you do not have to simplify it. Yay, yay, right? No, correct. Yeah, you cannot use, for the middle one, you cannot use the one that is further away or the one straddling on either side. As a general method, that is frowned upon. Okay? So it might seem kind of arbitrary that we could do it over here when they're equidistant. But over here, I mean, what if this one here wasn't 0.7 away? What if it was like 5 units away? That's a dramatic case, right? Then you would say it's too far to be relevant, really. So we try to use the one that's closest to it, but if they're both, 5 units away, then maybe we don't even approximate it, because we can say that the numbers that are on either side are too far away. It's just an approximation. So this is what we call best practice. And the best practice when it's not equally spaced is to use the one we want and the one that's closer to it. Okay? But again, that's why I said in recent years they've kind of gone to this method. They're giving you a value that's not in the table, and you would use the ones that fall on either side. So in that case, there's only one method, and you're using the two around it. Okay? I think they realize sometimes that people can interpret things different ways. All right, last question here. From the information given, is it possible to determine both the time and the position of the bug when it is farthest away from the origin? Why or why not? Well, if you look at the data points, it should be farthest away from the origin when the magnitude of S is the biggest, right? At least from the table. So that would be 48.2. So could you then say at t equals 2, whatever, is farthest away from the origin, and at that time it's 48.2 units away? The answer is heck no. Why? Very good. The function is continuous, and these are just a sample of some of the points. We have no idea what the function's doing anywhere in between these points. It could go from 48.2 up to like 5 million at like 2.3 and then come back down to 45, right? We have no idea. So we would say no, since S of t is continuous, and we only have, you can say, what did you say, Kevin? Actual points, or we could, yeah, what did you say? I'm sorry, louder? Sample points. Yeah, I like that. We only have sample points. Yeah. And then if you want, you can even add the position values the position values could be anything in between the data points that are given. That's another answer that you could use. Okay. So the fact that it's continuous is important. If it wasn't continuous data, like if these were the only data points, then we could say, heck yeah, the max is 48.2. What situation would that like be, where we have actual data points and it's not continuous? Like your grades in class, right? Your grades in class. This could be like different times, and those could be your grades. Wow. You really need to study harder, right? But look at how, I give you a grade of 38.2, right? Instead of just a 38. I'm nice. Yeah, so you get the idea. There are cases where you have discrete data points, and that's what I was going to write down here. We only have a sample of discrete data points, so these are continuous. They're not discrete, actually. All right, I'm going to quit talking. My throat's getting sore, and we made it through example 9, so hopefully you got some of those answers on your own. When you come back from lunch, we'll do something else. I'd like to start the next section.